folks. Welcome to lecture 26, where we will start our discussion on waves. We start with the simplest, or actually the most widely used wave motion, the topic of simple harmonic motion. To start a wave, there must be some disturbance. That disturbance is basically what is known as oscillations. Oscillations are the root cause behind any waves. So, for example, if you think about water waves in the sea or the ocean, the water is forming waves because of particle vibrations, the water particle or water molecule vibrating up and down as the wave moves along. So these vibrations are very simple examples of oscillations. You can also think about oscillations in the picture of a child's swing. When a child swings back and forth from the middle position to a higher position in each direction, but then the motion is oscillatory because it goes back and forth. You go up, you come down, and you go up and you come down. So this kind of back and forth or repetitive motion is also known to be as periodic motion. Oscillations are in fact periodic motions. Periodic basically means something repeating after a certain period or time, and this period is denoted by a capital T, which this is nothing but a certain time after which any oscillation repeats itself. And oscillations are usually counted in cycles of motion because it is repetitive or cyclic motion. Hence, the number of completed cycles of oscillation in one period, the period being the time taken to complete before the oscillation repeats itself, is called the frequency. Okay, so this is something that we term for oscillations. The frequency of an oscillation is nothing but the number of completed cycles in one period. Hence, frequency is related to the time period as in this equation, F equals 1 over capital T. The unit that we use for frequency is Hertz, after the German physicist, and 1 Hertz is basically equal to one completed cycle over 1 second. Alright? Now, let's look at simple harmonic motion a little bit more closely. A simple harmonic motion is a very basic example of oscillations, as we have mentioned. That is a back and forth or repetitive motion. You can simply think of a mass connected to a spring which is fixed at one end to this wall here, and we can think about holding the mass at an extension of delta x. Okay, we have previously met this kind of system when we talked about Hooke's law, and this is exactly how Hooke's law works, but we have avoided the discussion of Hooke's law to much extent using forces and acceleration, because as we will see now, the acceleration is not constant, and our kinematics were only solvable for constant acceleration. Okay, so if you displace this box away from the equilibrium length of the spring and extend or stretch the spring up to extension of delta x, then you're displacing the spring away from its equilibrium length in this rightward direction. Hence, as we know, the spring will exert force that is opposite to this displacement, dictated by Hooke's law. So as the spring extends in the rightward direction, the force is exerted in the leftward direction, as shown. Now let's draw a free body diagram to investigate what is happening. And these are the forces. The y direction is not really important for us because there is no motion in the y direction. In the x direction, what do we have? We have the spring force being exerted by the spring on the block. And if you write down Newton's second law equation, choosing rightward direction to be positive, we get negative spring force equal to negative mass times acceleration, because if you let go, the acceleration would also be in the negative direction. This spring force is, as we know, is nothing but k delta x, as Hooke's law tells us, and that is equals to m times a, and the negatives are on both sides because of the direction in which they're moving. Alright, this spring force is now going to be known as restoring force. What is a restoring force? What does it do? Restoring force basically restores equilibrium. It restores equilibrium, right? Because since there is the oscillatory motion is repetitive, to make things keep repeating, something needs to get it back to its original state, and then from there it will repeat itself again. For example, if a child swings this way first and then comes back to the original position where it started from, this would be only possible if there is a restoring force that is making it come back to its original position, right? And then it will oscillate from that position again. So that is why for any oscillatory motion there is a restoring force, and that's how simple harmonic motion works. It keeps repeating because of this restoring force, and in this case the restoring force is due to the spring. Alright, moving on, let's look at the spring motion a little bit more closely. If you hold the spring block system at a displacement of delta x and then let it go, the block will first start compressing and going back to the equilibrium length. When you're holding it here, the speed is 0, while if you just let it go and the speed starts from 0 and starts increasing while the acceleration is pointed in the leftward direction. So the acceleration, remember, is connected to the spring force. So as spring force decreases, the acceleration must decrease because they are directly related. As the spring extension goes down, the spring force goes down, hence acceleration starts decreasing from this starting position. When the block system reaches equilibrium, acceleration goes to 0 because there is no more restoring force. Since the restoring force has done its job, it has restored the spring to its original length here. So the acceleration also goes to 0 because the restoring force has gone to 0. Alright? But remember, the velocity started from 0 and hence it started increasing when you let it go. At equilibrium position, the velocity is at a maximum value. Okay, let's call it v. Alright, and which direction is it going? It's in the negative direction because the motion direction is negative, and because we have chosen rightward to be positive. Alright, from this equilibrium position, since you initially put in some energy in the system by extending it, as we know that us or spring potential is 1/2 kx squared. So if you may put an extension in the system, you're actually increasing the potential energy of the system. Since you put in some energy in this spring block system in the beginning, therefore when it reaches equilibrium, the energy doesn't quite run out. Hence it will keep going. It will keep going into a compression state and reach a maximum compression. At this point, the velocity keeps decreasing as you go along compressing it. Alright, and so the velocity cannot be any more than 0 once you have reached maximum compression, because you're not going anywhere beyond this point. So at this point the velocity has gone to 0. Alright, but what happens to acceleration? At maximum compression, the spring will start to push back. Right, the spring will exert restoring force again because you have compressed the spring beyond the equilibrium length. Since there is a restoring force appearing again, there will be acceleration appearing again in the direction of that restoring force. So at this point, the acceleration would be directed to the positive direction. And then it will reach equilibrium again, where acceleration will again go to 0, and the velocity will return to its positive maximum value, because now it's positive because it's moving in the rightward direction. Alright? So to understand more about this kind of motion, it's better if we draw graphs. So if we draw the acceleration time graph of this spring block system, we see that this acceleration started from a maximum negative value in this position right here, and then went to 0 when it reached equilibrium length. So this is acceleration time graph. If time started from 0 initially, then at time 0 the acceleration was a negative a. Alright, and it started going towards the equilibrium where the acceleration went to 0, and then kept increasing as it started compressing again, and here at maximum compression it reaches maximum acceleration, positive a. From there the spring starts relaxing again as the spring extends out back to its equilibrium length. So from there it will go back to 0 when it reaches equilibrium, and then if it goes beyond this point and keeps extending out, then the acceleration will increase again in the negative direction. Right? What about our graph for if we want to graph the velocity. If you want to graph velocity time, we see that velocity in the y-axis and time in the x-axis. Velocity started from 0 when you held it at rest, and then when you let it go, the velocity was pointed towards in the direction of motion, which is negative. So the velocity increased in the negative direction from 0 until at equilibrium it reached a maximum value of v, actually negative v, because if you consider the direction still towards the negative x-axis. From then on, as it went on towards compression, the velocity kept decreasing to 0. Alright, it kept decreasing to 0. At maximum compression, the velocity has gone to 0 here, and then from beyond that, as the string extends out, the velocity keeps increasing. Alright, and then at equilibrium, the velocity went to a positive maximum value, and if the string of the spring block system extends out again, it will keep decreasing like before, okay, and it will reach 0 again at maximum extension. Alright, so this is how velocity looks. How does position look? Well, if we draw a graph for position, then we will see that the xt graph, or actually delta x time graph, would look like it started from a maximum amplitude or maximum displacement, and then kept going to 0 as it reached equilibrium length, so no extension. So it started from a maximum extension to 0 extension, and then maximum compression, and then went back to equilibrium length, so 0 compression or extension, and then it starts extending again. This is how a position time graph looks. So the relationship between each of these graphs is, we can see that these are actually graphs of trigonometric functions, or they are what we call sines and cosines. So this is a negative cosine graph. The graph for acceleration is a negative cosine graph. The graph for speed or velocity is a negative sine graph, and the graph for position time, or delta x time over time, is a positive cosine graph. Okay, so these are trigonometric functions, and we see that we did not talk more about acceleration when we talked about Hooke's law, because this acceleration is a curve, and for curves at every point the gradient is changing, hence acceleration isn't constant. So none of our kinematic stuff is actually viable in simple harmonic motion. Hence it is only logical to define how we understand or calculate acceleration, velocity, and position for this kind of motion, for simple harmonic motion. But so far we have just identified the fact that acceleration and velocity are not lined up. So velocity and acceleration, they are out of sync. Okay, out of sync or out of phase. Okay, so this is a new term that we are learning, and this just means that if we look at the graphs here, when the acceleration was a negative maximum, the velocity was 0. When the acceleration went to 0, the velocity just came to negative maximum. Therefore, all this means, out of sync means, is that velocity is lagging or is behind the acceleration. Alright, velocity lags behind acceleration. Now let's look at how we calculate all these acceleration, velocity, and position for simple harmonic motion. Well, it turns out that to find correct expressions for position, velocity, and acceleration in simple harmonic motion or oscillatory motion in general, you would need calculus. Since this course is not permitting us to use calculus, we will just take some things for granted. So the expressions for xt, vt, and at are as follows. If you can look at the xt graph, we can get a more clearer picture for what we mean by period and maximum displacement. So if you hold the block away from the equilibrium position of the spring at a distance of minus a and then let it go, then this a or minus a, this is what we call the amplitude the maximum displacement from equilibrium position is what we call the amplitude. And so x max, the maximum displacement away from equilibrium, is a amplitude. Okay, so if you have this expression to find position for simple harmonic motion, x is a function of t, so for any point in time, the position of x is calculated using this formula. The x max is nothing but plus minus a, which is the amplitude of this motion. What is actually the argument of cosine and sine and cosine for all of these x, v, and a? Well, since the cosine graph, if you have already taken a very basic course in trigonometry, we know that every angle 2 pi radians, the cosine graph and the sine graph, they all repeat their motion. So this is this whole part of the curve. This is one full cosine curve, and after 2 pi radians, so from here to here is the angular displacement of 2 pi radians. After 2 pi radians, the curve basically repeats its shape. It's the similar thing for sine as well. So, and we know that for repetition of the curve, we say that the number of cycles produced in one time period is what we call the frequency. So here inside we need a dimensionless quantity, because ultimately we would want the dimension of x to be determined by x max, which is units of length, and the units of velocity should be determined by some velocity, and units of acceleration should be determined by some maximum acceleration. So we need this quantity to be dimensionless. So how do we do that? We insert 2 pi. Every 2 pi the curve repeats, and what is the time period for its repetition? It's capital T. So the argument of sines and cosines here is 2 pi over capital T times small t, which is any point in time. Alright, so we have 2 pi over t. But what is Vmax and what is Amax? Vmax can be found by using energy conservation, that we will shortly look at, and Vmax turns out to be this expression right here. Alright, so Vmax depends on K, which is the spring constant, m, which is the mass of the spring, which is the mass of the block, alright, and a, the amplitude. And what is at? Well, at means the acceleration is dependent on some maximum acceleration, and maximum acceleration is found using this equation, which is dependent on k, m, and a. Alright, now let's look at energy conservation. So if there is no friction or any other dissipative forces, then energy is conserved. That is not only true for simple harmonic motion, but any motion, any kind of motion in general, because energy, as we know, cannot be created or destroyed. It can only be transferred and transformed from one point to another, or one form to another. So the maximum energy it occurs at 2 points. One, when you have maximum displacement away from the equilibrium length of the string, which is at its amplitude, because we know that spring will have spring potential energy defined by 1/2 kx squared, and this ax becomes a, the amplitude. So you cannot have any energy higher than when the block is at amplitude length. Okay, so this is one instance when you have maximum energy of the system, dictated by completely the potential energy of the spring. Or you can have the maximum energy when the velocity is maximum for the spring block system. When does this occur? When the block is back to equilibrium length, and then that is the point where you have maximum velocity, which is dictated by the kinetic energy. So for maximum velocity, you will have maximum kinetic energy. So what does this come out to be? This comes out to one simple fact, is that the maximum energy can only be equal to the maximum potential energy at its amplitude, or the maximum kinetic energy at equilibrium. So these two have to be the same. Why? Because the only energy you can gain after you let the system go is the maximum potential energy you had at the beginning. The maximum kinetic energy can only be equal to the maximum potential energy of the spring at amplitude. and vice versa. The maximum kinetic energy can only be the maximum potential energy when the spring is, say, compressed. It will not go beyond this compression point. So the maximum energy can only be equal to each other. Okay, all of either all of potential energy has transferred to all kinetic, or all of kinetic will transfer to all of potential. They cannot exceed each other. Okay, and anywhere in between these two extreme points, that is at amplitude or at equilibrium length, anywhere in between amplitude and equilibrium, let's say this position right here, at anywhere here, the energy of the system will be a summation of kinetic and potential, and that will be equal to the maximum energy of the system available to it, okay, which is either maximum potential energy or maximum kinetic energy, whichever you want to consider. Alright, so anywhere in between, it will be a summation of kinetic and potential. We are talking about horizontal spring mass systems here. If the spring mass system is vertical, be sure to add in what we call the gravitational potential energy as well, okay, because then you would need to contest with gravity for your energy of the system. Now let's look at some other things, then we will jump into an example. The fact that we have k over m in expressions for Vmax and Amax tells us something that indicates to us that k over m must dictate some form of motion of this of our system, right? Then let's look at k over m a little bit more closely. What is k? K is the spring constant of the spring. M is the mass attached to the spring. So m is the mass of the block. Now, for a system where you have a constant mass, for a system like you have already chosen the mass and you hold it at a constant amplitude, or you displace it at a certain known length, if you change the springs, that is, if you're changing the spring constant with an increasing k, we see that both the Vmax and the Amax increases, because with increasing k you will have higher restoring force that will result in a higher acceleration, that will result in a higher speed, and then that would mean cycle finishes faster. Alright, finishes faster when you have k increasing, right? For a higher k or a larger k, cycle finishes faster. So frequency must be faster, alright, must be higher. And for what about m? So let's say you are not changing the spring, but you are changing the block attached to the spring and keeping the amplitude the same, and you're keeping also the spring same. So when mass has increased, when you're increasing the mass, the spring cannot exert a greater force just because you're attaching the mass that is bigger. So the spring exerts the smaller force because you're keeping the spring the same, you're just increasing the mass. So for the same spring, it is not possible to exert more force for a larger mass. So the smaller force will result in a smaller acceleration, and the smaller acceleration will also result in a smaller maximum speed, and hence the cycle will finish slower. Alright, meaning the frequency would decrease when m is higher, when the mass is higher. From that stems these expressions of frequency and time period. Frequency is defined is found by 1 over 2 pi square root of k over m for a mass spring system like this. From there we can just write down what our time period is, because time period, as we know, is 1 over f, and we can just invert this whole expression. From there we can go forward and define what angular velocity is or angular frequency is in the context of oscillations. We met angular velocity before. It is basically the change in angular displacement over change in time. In the context of oscillations, what angular velocity becomes angular frequency, because what we want is how fast the cycle is being completed in the angles inside these sines and cosines, the arguments of sines and cosines. It turns out that omega angular frequency is defined as 2 pi times the frequency. Okay, so once we found the expression for frequency, if you plug that in, we get an expression for omega, or angular frequency, for a mass block system. Is related to the spring constant of the spring and the mass of the block. This in turn lets us know that the time period is 2 pi over t. So if you have this expression for t and you multiply 2 pi to it, or divide this, you divide 2 pi by this, then you get omega as well. So whatever is inside the arguments of sines and cosines just is 2 pi over t, just becomes omega. Alright, so omega is nothing but 2 pi over t. Alright, omega is 2 pi over t. So in total, we have all these formulas for oscillation or simple harmonic motion. Okay, for simple harmonic motion, we have all these different expressions for velocity, acceleration, or maximum velocity, maximum acceleration, position, frequency, and so on and so forth. Now let's look at an example. The question gives us a mass attached to a spring, and this oscillates, creating a simple harmonic motion, and the amplitude of the oscillation, that is the maximum displacement from the equilibrium length of the spring, is given to us to be 4 centimeters, which in SI units of meters is just 0.04, and a time period of this oscillating system is 2 seconds. We are asked to find what is Vmax. Now our first go is to go and see what Vmax is, what the equation for Vmax is. Vmax is equal to omega times A, the amplitude times the angular frequency. What is angular frequency? We don't know angular frequency, so we look for an angular frequency equation. Well, we see that angular frequency here we have found to be 2 pi f, right? But that's not helpful because we also don't know the frequency, right? So what is our next goal? We know that this is a spring block system exhibiting simple harmonic motion. So we go to the fact that angular velocity is directly related to k and inversely related to m by this expression right here, right? So angular velocity is nothing but square root of k over m times a for Vmax. Now we look at what we are given. We are given the mass of the block, which is m here, 3 kilograms, fine. We are given the amplitude, but we don't know k, and we are asked to find Vmax. So how do we find k? Well, k is the spring constant, and we know something else, alright? We know the period of oscillation, okay? So what do we do with that? We recognize that the period of oscillation is related to mass and k, so we can use that fact, right? Or we can directly choose to use this equation, whichever one you want to do, but ultimately we have this. Time period is equal to 2 pi times square root of m over k. What is the time period? Time period is given to us as 2 seconds times 2 pi is equal to 2 pi square root of mass, which is 3 over k. Alright, the 2's can go away and we can cross multiply both sides. So square root of k goes to this side, and on that side we have 1 multiplied by pi times square root of 3. To find k, we square root both sides. This leaves us with k on this side, and on that side we have 3 times pi squared, which gives me a spring constant of, let's not approximate, let's just keep it like this, Newton per meter squared, actually Newton per meter for spring constant k. And then we find out what Vmax is. How do we find what Vmax is? We just directly go to our expression for Vmax. Vmax is omega times A, as we have seen here. So omega times A, we have found out what k is. So the square root of k, 3 pi squared over m, which is 3 kilograms, times amplitude, which is 0.04, right? The 3's can go away and we are left with 0.04 times pi. This comes out to be 0.126 meters per second. This is the maximum velocity of the oscillating block. Now let's look at a second part. Now the question asks in the second part, what is the speed at x equals 1 centimeters or 0.1 meters? We know that the amplitude is 4 centimeters, so 1 centimeter is in between delta x equals 0 and delta x equals 4. So anywhere in between the equilibrium length of the spring and the amplitude of the spring, we have seen that the energy distribution is as follows. The maximum energy is distributed between the kinetic energy of the system and the potential energy of the system, anywhere between the two extreme points. What is the maximum energy? It is either the maximum potential energy or the maximum kinetic energy. We can use either. So let us just use the maximum potential energy, which is 1/2 k amplitude squared. That is distributed among kinetic energy 1/2 mv squared at x equals 1 centimeters and the spring potential energy at x equals 1 centimeters. So 1/2 k delta x squared. Delta x in this case is what is delta x? Well, delta x is what is 0.1 meters, what is given to us, right? 0.01 meters, and that there should be a squared here. So you can cancel out the halves from all of these, and we know what mass is. Mass is 3 kilograms. We have found k to be 3 pi squared. We know what a is. A is 0.04, so you can square it. Basically what we end up with, if you keep solving this equation, is v equal to square root of 0.0016 pi squared minus 0.0001 pi squared. This gives me the speed at 0.01 meters is 0.122 meters per second. Alright, so this is how we solve simple harmonic motion problems involving spring block systems. I hope this lecture made sense. Thank you very much.